Question 21 says a paramagnetic sample shows a net magnetization of 6 ampere per meter when placed in an external magnetic field of 0.8 Tesla at a temperature of 10 Kelvin. In order to have same magnetization when the sample is placed in external magnetic field of 0.4 Tesla, the temperature in Kelvin should be. Well, the question is from the topic magnetism and matter, and we know that for a paramagnetic material, when of course it has not reached the saturation magnetized level, the expression for magnetization is that M is in fact equal to C into B divided by T. C is the Curie's constant, B is the magnetic field, the external magnetic field, and of course T is the temperature in Kelvin of the sample we are talking about. So in our case, what we have is B1 by T1, because the magnetization level has to remain same, is equal to B2 into T2. So the value of B1 in fact is given as 0.8 Tesla and temperature T1 is 10 Kelvin. So the value of temperature T2 is then B2 into T1 divided by B1. The value of B2 is given as 0.4 Tesla and other values we have just talked. So value of T2 will be then 0.4 multiplied by T1, which was 10 Kelvin, divided by B1, which in fact is 0.8 Tesla. And we find that this is coming out to be 5 Kelvin. So that means answer to question 21 is 05. Pretty simple, isn't it? But of course one had to know the formula that magnetization for a paramagnetic material is given by C into B by T. Time now to go to the next question. Question 22 says a semicircular ring of mass M and radius R is initially at rest in a vertical plane as shown. It is free to rotate about horizontal axis AB as shown. The angular velocity of the semicircular ring, if it rotates by 180 degree from initial position shown, will be n into under root of g by pi r. The value of n is. So we have to apply the concepts of rotation. In fact, we have to conserve mechanical energy, and as the ring rotates by 180 degree, well, the gravitational potential energy is converting into rotational kinetic energy. So first of all, we need to find the expression for the loss in gravitational potential energy. And for that, we recognize that the center of mass of the semicircular ring from the center of curvature is in fact at a distance of 2r by pi, where r is the radius. So this is the distance of center of mass from C. As it rotates by 180 degree, the position of the ring will be something like this, isn't it? So that means the center of mass would have come from its original position. It would have come down by 2 times of 2r by pi. So that means 4r by pi is the distance by which the center of mass of the semicircular ring has come down after it has rotated by 180 degree from initial position. So the loss in gravitational potential energy is mg into the distance through which the center of mass has moved down, and that is 4r by pi, and this must be equal to half I omega square, where I of course is the moment of inertia and omega is the angular velocity. Now what about the value of moment of inertia I? In fact, this would be equal to mr square by 2. So this is mr square by 2, because we can get this result by using principle of superposition. We can put one more ring like this, or rather one more semicircular ring like this, so we have a complete ring whose mass would be 2m and whose moment of inertia about an axis perpendicular to its plane passing through its center would be 2mr square. So half of that, and so by applying the perpendicular axis theorem, the moment of inertia about a diameter of each one of these two semicircular rings can be found as mr square by 2. So that means we have mg into 4r by pi equals 1 by 2 mr square by 2 into omega square. And remember, this small m is in fact the mass, which in fact has been given as capital M. So there is no difference between small m and capital M here. So now let's find the value of omega. We get omega square as we shall have here 16, and we can see that one r will cancel, and of course m cancels, so we have 16 into g divided by pi r. That is the value of omega square, and the value of omega itself would be then 4 times under root g by pi r. So the value of n, if we compare with the expression given, is 4, but according to the format of the question we have to put 04. So the question 22 is done. The answer is 04. It's time now to look at question 23. Question 23 says, blocks A of mass small m and B of mass 2 times small m connected by an ideal spring of force constant K rest on a smooth horizontal plane. Block B is shifted a small distance x to the left and then released. The velocity of the center of mass of the system of A plus B after block A breaks off the wall is x by 12 under root pk by m, and we are supposed to find the value of P in this expression. So well, what's happening here is that when the block B is shifted towards left with distance x, the spring is effectively compressed by distance x, and so the potential energy stored in the spring becomes half k x square. So k is the spring constant or force constant, and x is the compression in the spring. Now, well, as long as the spring has not come to its natural length, block A will remain at rest, okay, and after that only A will start moving. So we have A at rest throughout this duration. When the spring regains its natural length, in fact after that moment only, A will start moving. So till that point A is at rest, and we can find the speed of B after the spring has regained its length by conserving mechanical energy, and that equation is half kx square equals half mass of B, which is in fact 2m, into Vb square, and this gives us the value of Vb as k by 2m, and we have to take a square root, and of course there is x here. So this is in fact is the speed of block B, and it's moving towards right at that moment. Now we have to find the velocity of center of mass of the system of A plus B. So velocity of center of mass VCM is m1 v1 plus m2 v2 divided by m1 plus m2. So VCM is m1 v1, that in fact is 0 for block A, and for the other block it is 2m into Vb, which is x into under root of k by 2m, and of course we need to divide this by 3m. So we see that the value of Vb is coming out to be 2 by 3 x under root of k by 2m, and well, we need of course to compare this with the given expression. Now to do that, what we can do is, if we equate this in fact with x by 12 into under root of pk by m, what do we have? No, let's just equate these two, and what we are getting is 2 by 3 into 1 by root 2 in fact is coming out to be root p by 12. So this cancels, we get 4 or 8. So in fact root p is coming out to be then equal to 8 by root 2 or 4 root 2, and if we square both sides we have value of p coming as 32. So that means for question 23 answer is 32, the value of p is 32. It's time now to look at the next problem. Question 24 says a pipe of length 85 cm is closed from one end. If the speed of sound is 340 meter per second, then the number of possible natural oscillations of the air column in the pipe whose frequencies lie below 750 Hz is. So the question is based on oscillations of air column in organ pipe, and in this particular case we have a pipe which is closed at one end and open at the other end. So in this particular case the fundamental frequency f0 is given as speed divided by 4 times the length of this open pipe, and let's evaluate the value of f0, the fundamental frequency. The value of v is given as 340 meter per second, so we have 340 divided by 4, and the value of L0 is 85 centimeter, which in fact is 0.85 meter. So this is coming out to be 340 divided by 3.4, and which in fact is 100 Hertz. So 100 Hertz is the fundamental frequency, and it's a closed pipe, so it will only have the odd multiples of the fundamental frequency as its natural frequency. That means the frequencies which are allowed are 100 Hertz, then 300 Hertz, then 500 Hertz, then 700 Hertz, well 900 Hertz, and so on and so forth. But we have to look at frequencies which are less than 750 Hertz. So these are in fact the 4 frequencies which are less than the 750 Hertz frequency, right? So that means the number of possible natural oscillations are in fact 4, which correspond to frequencies 100 Hertz, 300 Hertz, 500 Hertz and 700 Hertz. So answer to question 24 is 04. Let's now go to the last problem of this test. Question 25 and the last question of this test says a person carrying a vessel emitting a note of 306 Hz is running towards a reflecting surface with a speed of 5 meter per second. If the speed of sound is 345 meter per second, the number of beats heard by him in Hertz are. Well, so the person is in fact carrying a vessel, and so one frequency that he will hear is 306 Hz, the frequency actually emitted by the vessel, because he is running with the vessel. And let's look at the Doppler effect, how the frequency is modified. So first of all, we see that the frequency received by the reflecting surface is given by F1, and that is the frequency emitted by the source, into the speed of sound, which is 345 divided by 345 minus, well, the velocity of the source, and the velocity of source is given as 5 meter per second. So this is the frequency heard by the wall itself, and next time the person becomes the observer, this is the frequency that the wall is emitting again, and since the person is moving towards this wall, the frequency that he gets or perceives from the wall would be in fact F1 into, this is F1 into 345 plus 5, because now is the observer, divided by 345. So this means that the other frequency, the frequency from the wall that he is getting, is then equal to F0 into 345 by 340, and we have to multiply this by 350 divided by 345. So this is, now we can see that this is F0 into 35 by 34. So the difference in the two frequencies, in fact, that will be the beat frequency. So the beat frequency, let's say the beat frequency in fact is equal to F2 minus F0, or which means it is F0 into 35 by 34 minus 1. So in fact this is F0 divided by 34. And let's look at the value of F0. F0 was given as 306 Hertz, and this of course we divide by 34, and this is exactly 9 Hertz. So the frequency, the beat frequency in fact heard by the person would be 9 Hertz. So our answer would be 09 for this particular question. And in fact, with that we have come to the end of this discussion. I hope you found the solutions useful, helpful. Thanks for watching. Take care and bye.